Suresh. He's going to give an introduction, and we'll kind of go from there.
So welcome, everyone. My name is Suresh Srinivas. I am one of the founders of Hortonworks. One of the areas that I focus on is streaming. Right? So stream processing and streaming is taking the big data world by storm. Right? No pun intended. Right? If you see, there are a couple of trends that are happening, with streaming. The first one is clearly, we started with Hadoop long back at Yahoo. It was all batch-oriented processing, right? You had daily reports and that kind of stuff. That is what Hadoop was crunching. Now, the world is changing. It went from daily to hourly to every 15 minutes. But people want real-time what's going on in their enterprises, right? So that's one key trend. The second trend is streaming plus predictive analytics, right? So with machine learning. And streaming together, now you can not only consume the data as it is happening, you can also use predictive analytics to understand the data and act on it, right? So this will power the next generation of automation, right, at an enterprise scale across all the events. The third thing that is somewhat overlooked is all data gets created as small data, right? And so if you see in the past Hadoop world, you accumulate all this data and then you do big data crunching, right? So streaming is a way of keeping the small data small, right, and acting on it, on a real-time basis. That is also one of the most efficient ways to process this data as well, right? So those are three trends. Today we have a big lineup, and we have a couple of sessions. In the first session, Hugo, who is newly minted Storm committer, is going to talk about Storm 1.1 release and the exciting things that have happened there. In the second part, we will talk about some of the lower level details of Storm and the worker improvements for taking Storm to the next level of performance and what's going on there. Now, any project, it's very important to look at the use case and how customers are using it, right? So from that perspective, we have Karthik from Walmart, and he's going to talk about how they are using Storm, right? And that is a great learning both for users of Storm and people who are developing Storm, right? And in the last part, and this is what I'm really excited about, we are building two new projects, one for one called Streaming Analytics Manager, or Streamline, and Schema Registry. The goal of this is to take the massive, real-time, scalable computing you have in Storm and make it easy to use and easy to develop against, right? So that is the trend that big data is moving towards, right? Now we used to build complex platforms. Now we are making them super easy to consume. I highly recommend attending that last session. How many of you are going to stay till the last session? Otherwise, we'll flip it around, right? So, and we'll also ask you to pay for the pizza, right? So if you're not going to stay back, right? So, so how many think that we should flip it around and do it earlier? Okay, so we'll, yeah, yeah. So now the last thing that I want to talk about is Storm as a community is a very inclusive community. It's a great community to work in. And the same community is powering Stream Analytics and Schema Registry, right? So a community is only as good as the participation it gets. And so given this community is very easy to work with, I welcome all of you to take a look at these projects, Storm, Schema Registry, and Streaming Analytics, and participate there, right? So it's a very good community to work with. So with that, I will hand it over to Hugo for capturing Storm 1.1 details.
All right, welcome everyone. Yeah, Suresh did a great introduction. The only thing he didn't say is Hortonworks is a pretty good place, and we have a pretty good team. Anyway, yeah, so indeed, Storm is a very inclusive community. They let me in. So we are. Can you the mic here? Oh, okay, better. So yeah, so Harsha is the tech lead of ours. We are all in the streaming team, Harsha, Roshan, and me. And then we have a visiting guest from the Walmart Labs. So we are very active in the Storm community. And I'm gonna walk you through a little. Hmm? Oh, it's flipped. No. Oh.
So by the way, that's the streaming analytics platform that we are building. So this is what it looks like. So Harsha will cover that.
All right. So yeah, so this is all built on top of Storm. So Harsha will talk a lot about this. So Apache Storm. So I'm going to give a quick introduction. Everyone knows pretty much what Storm is. Reliable, distributed computing framework, fault tolerant, that gives you predicted computation, and is horizontally scalable. This is as much as I can summarize it. So Storm started in 2010 at a company called Backtype. Nathan Mars drove the project back then. It was the first streaming framework of its kind. In 2011, Twitter acquired Backtype and deployed Storm in their backend to perform a lot of their computation in a scalable way. In 2013, Storm was open sourced into Apache, and he has a large imprint in a lot of production environments, some very large scale. For example, Yahoo has it running in over 3,500 nodes. Alibaba processes over 1 petabyte of data per day with Apache Storm. So a really quick highlight of the very early releases. 0.9 was a really important release because was when Apache became a top level project. It was the first official release, and you know some of the first improvements were expanding Kafka, GFS, and HBase integration. Then 0.10 was when it became like really more enterprise ready. We start supporting multiple tenancy, rolling upgrades. We improved logging, obviously, it's very important for debugging in production. And we added more support for external data sources like JDBC, Event Hubs, and Hive integration. Yeah, so Storm 1.1 was a major release with a lot of innovations. So streaming from like Yahoo's 3,500 node cluster, they were hitting some bottlenecks in Zookeeper. So they introduced, or the community introduced, Pacemaker to replace Zookeeper for heartbeat management. There was added security in terms like Kerberos and digest authentication. The single point of failure up to that point was Nimbus, which was the master node, if you will. Up to that point was a single point of failure. Then it was added into like a high availability, or we call it Nimbus AJ. Then we added supervisor health checks and resource-aware schedulers, such that you can assign your tasks to the workers in a more efficient way, taking into consideration CPU and memory consumption of the specific machine. Other improvements were stateful bolts. This is a very important internal detail, which is the building block for things like checkpointing, snapshots according to the ABS and channel import algorithms, which are cited in the resources slide, which are important for streaming windows like sliding, tumbling, watermarks, out-of-order tuple processing in case you're processing tuples based on a real-time event. And then like improving on some of the requirements from customers. That Storm had some challenge in terms of like debuggability and deployment. We added dynamic log levels, distributed log surge, worker profiling. You can basically profile any distributed worker JVM, from the Storm UI. And we kept on building support for external data sources like Solar, Cassandra, Elasticsearch, and MQTT. So Storm 1.1 is the main focus of today's presentation. It also has a lot of improvements in terms of like features and stability. One of them being Storm SQL. Oh, and a quick parenthesis here. I'm just gonna walk you through the bullet points and I'll go into detail in each one of them. So Storm SQL, Apache Kafka integration supports for Kafka consumer like 0.10 onwards, which is known as a new consumer API in late language. PMML support, Druid integration, OpenTSB integration, Kinesis, HDFS, and other enhancements like in the Flux, which is the descriptive language to define topologies, topology deployment in itself, and more improvement in the resource-aware scheduler. Yeah, so what is Storm SQL? So Storm SQL is basically a way to define your topology using a SQL-like query. So this is very important because it abstracts a lot of the programmatic details involved into creating a Storm topology, like namely spouts and bolts. It uses the calcite library for query parsing and planning, and once you deploy your query, SQL is compiled and transformed into the Trident topology, which is abstracted by multiple storms and bolts internally. Yeah, so right now we provide support for Kafka, Redis, HDFS, and MongoDB data sources. It's easy to extend by implementing the iSQL Trident data source. So some of the functionalities that stream from streaming SQL are tuple filtering, projections, comma separated values and tab separated values, and every input and output formats, user-defined functions, and you can have finer control over the parallelism of the generated components behind the scenes. So basically, if you hit bottlenecks, you can dig into the internal details of how SQL is broken down into Storm primitives and optimize each one of those. So here is a quick example of how you can implement an aggregate function. This is a very simple string concatenation. You basically just create a SQL query called concat function, create function, whatever name you desire, and you provide a Java implementation for that function. So, and now I'm also going to walk you through a Storm SQL example. So the idea here is you have some log files that are written into a Kafka topic, and the goal is to read the contents of those log files from the Kafka topic, filter everything except log events, and write those log events into another Kafka topic. And the way to do that is, I hope it's readable. So basically, you create a table, Apache _logs, which is where you're reading your log files from. The columns is basically the structure of your log file. And then you create another table, which is basically the abstraction for the Kafka topic where you want to write. And once again, the columns define the structure on how you want to write the contents into that Kafka topic. And you can specify properties, namely, serializers, so you can write to Kafka, and other important things like the bootstrap servers, whatever it may be. And then the way to do it is like you have this insert query, which basically just tells, write me into the topic. It's called Apache errors, reading from Apache logs. And and you have some powerful features like, for example, if you look at the status column is here up top, is a varchar, and you can cache it into an integer, right? So then, as far as one of the main uses of Storm is to ingest data. One of the main sources of ingestion of data using Storm is Kafka. So we have done a lot of improvements in terms of like scalability and also ease of use and support, as I said, the Kafka 0.10 APIs, or as they are called, new consumer APIs. So we support consumer groups, abstraction on how to map Kafka records into tuples, topic wildcards, multiple streams, and integrates with security environments. It also supports all the Trident abstractions. So this is a quick example. It's hard to read, but basically all I want to highlight here is it's very simple. You create a Storm topology with the Kafka spout. In the Kafka spout in the configuration, you basically set the group ID. You set the way you can retry according to an exponential backoff. You can plug in the tuple mapper to convert Kafka records into tuples. And you have a retrial strategy, and then you can support multiple topics per stream or multiple streams per topic. It doesn't matter, and then you can subscribe to to that Kafka spout using multiple downstream bolts. I'll be happy to discuss this at the end, and we're going to share the slides so you can walk yourself through this. Another big enhancement for Storm 1.1 is PMML support. So PMML is a predictive model markup language, which is basically a way you can describe a machine learning model that has been learned. Once your model has been tuned and learned, you can describe it using an XML-like descriptor language, and basically Storm can load those models and compute predictive scores for live tuples based on those models. And the model can be either uploaded directly or downloaded from a distributed cache supported in Storm. So this is another code snippet, so it's very simple. You basically just, the first line, you describe the output streams, and then you say, if you want to load it from the blob store, you do. You define the outputs of the model, and you define the bolt. So basically on the bolt, you pass the model runner factory and the output fields, and that's it. This is as simple as it gets. Other Storm improvements were Flux. It's now possible to visualize it in the Storm UI. It's possible to specify resource requirements for memory, CPU, and individual topology, as I said, resource-aware scheduling. Another big feature is Storm initially had the requirement of building Uber jars to deploy your topology. So right now, using the command line for each topology, it's possible to specify extra jars, just pointing them into a local location. It's possible to point to Maven repos for certain Maven artifacts and add additional repos. So this is quite powerful because basically it takes the burden of building Uber jars, you know, library version conflicts, all of that. So at last but not least, we hope that you are willing to test and play around with Storm 1.0. So we have a sandbox here at Hortonworks, and you can find the link here at the bottom where you can very easily download it and test. We have an entire built application using like tracking IoT data. At last, I'm just going to walk you through the main milestones for Storm, for Apache Storm 2.0. So one of them is the entire code base is finally be completely rewritten in Java. So initially there were several core implementations in Clojure, which some of them were already migrated in Storm 1.1, but the job is going to be completely finished for Storm 2.0. There are significant performance improvements, namely in the worker and thread model redesign. Roshan is going to talk in detail about that. Pretty exciting stuff about that. We're also working very actively in the Apache Beam integration, such that if you already have your production environment using Storm and you want to support it in Beam, it's going to be possible. Bounded spots is a requirement that strives from Apache Beam, so we're working on that. We enhanced metrics also to address some requirements from customers that they want Storm to be easier to use and easier to debug. So we're really very actively addressing those requirements. And other little things like worker class loader isolation, improved back pressure, and dynamic topology updates, which is a mix of overall improvements and ease of use for customers. And with this said, it's just the references of the slides I presented. I'm going to pass on into the next speaker, which I believe is Roshan. Is it Roshan? Okay, what happened here? Oh. What happened? What happened?
only for the live stream.
Can you hear me now? Yes. Okay, cool. So my name is Roshan, and so I'm going to be covering some stuff which is actually we're planning some redesign of some of the Storm worker, some of the execution engines of basically. So today, kind of, if you'll give me a second, switching mics. So we are failing over to another mic, hopefully. Can you hear me now? Okay. Yes, it's HA. So currently, Storm has been sort of the early horse in the streaming race, and it's kind of become a mature and stable system, especially works quite well in your production system. That's one of the things we often hear, that people have sometimes tried a different one and then sort of in production didn't work, and then they kind of went with Storm. So kind of it's a relatively mature and well deployed, very wide user base. And now you also see a lot of competition coming up, like you probably hear, a new streaming engine coming up every few months. And usually they're differentiating either in terms of features or performance or ease of use or some other aspect. So Storm has been catching up on features a lot. You'll see some stuff also coming up a little later in the presentations around ease of use related to developing Storm topologies. In this one, I'm going to be covering more on the performance side. So, when I was starting to look into performance, you kind of look at what the state of the systems around is. And one thing I noticed that pretty much everybody claimed that they're fast, right? Now, usually the typical way they do it is they say, here's our number and it's better than somebody else. But so I thought maybe we can look at it at a different angle. Let's just see how fast the hardware can actually do, right? So I did an analysis of the sort of the lower level primitives that are used to build these systems, and that's this Jira here, the Storm 2284 has a analysis. I wrote some programs by hand, compared it to the published numbers, and benchmarked some lower level primitives. And in short, the assessment was that there's a lot of gap between even the best numbers out there and what the hardware can actually deliver. So with that, started to look into what are the big factors that actually drive performance. So so some of the major dimensions are like throughput, latency, and resource utilization. I'll be talking largely on these two. And this is the Jira where actually much of this has been covered. Let me just briefly go over the list of things that we have sort of in the plan for this year. So I'll just hit them like really high level, not go them too deep. So for example, this is the two topics I'm going to try to cover today, which is actually restructuring the messaging system, changing the execution and threading models. Then we also have thoughts around adding non-replayable sources. So things like you could probably just take input from HTTP kind of sources or TCP or syslog, for example, which are not replayable if you're willing to drop data. We are looking into different ways of doing back pressure, much lighter weight mechanism. Elasticity, this is about actually being able to grow and shrink as required. So if you have more pressure coming in, then you kind of have more instances your spouts and bolts automatically spin up and then sort of shrink back. The primary thing there is that you need smarter ways to hint. Today we have like a parallelism hint which says I want 2 instances of the spout and 3 of the bolt and so on and so forth for each of those spouts and bolts. We need like a richer system so that the system can decide how to multiply the number of instances to scale out and then accordingly shrink back. CPU pinning, that's sort of ties into the threading model. Batching and vectoring. So batching is a way to sort of get more throughput typically, but batching comes with the downside is that sometimes you have to tweak the batch size to get the right balance in latency and throughput. So there are some thoughts here how to get around that so that the system batches dynamically based on what's available rather than some predefined batch sizes. Message timeouts is another sort of area where I had some thoughts around sort of thinking about it differently. I won't go into it now, but if you click through that, you'll find some of the details around that. Memory management, I'll speak about that briefly, but my observation was that this is a little bit harder to do if you're in the Java space. Okay, so these are sort of the 3 major areas for performance. These are sort of the critical areas. The first is the messaging system, then is the threading model, and finally the memory model, how you deal with memory. Messaging system, if you look at Storm really and you shrink it down to its like the bare minimal, it's basically a bunch of threads which are communicating with each other over message queues, right? Data comes in, gets processed by one thread, goes into a message queue to another thread, and so forth. So basically the message queue that you use here is really critical. We need bounded concurrent queues, something as fast as it can go, basically, as fast as the hardware allows to do concurrent messaging. And when to get like this super fast space lock-based queues don't work. They're just simply too slow. So what you need is lock-free queues, or preferably wait-free queues. If you're not familiar with those terms, it basically means that in both cases there's no locks, but in wait-free what happens is all contenders who are contending on some atomic operation, everybody succeeds. Nobody blocks, so there's no retries. In lock-free, there's a retry mechanism required. Only one guy succeeds. Threading model. So the basic crux of this is we want to reduce the number of threads. Reducing threads means also less synchronization. There are a few additional threads that are being used currently, which we are planning to get rid of. I'll cover that briefly. Also, since there's a continuous stream of data, there's no real need to do thread pooling. That was an observation. Basically, you just need a dedicated thread to which you can divert the data, rather than say, okay, there's some data there. Let's send this thread, then take the same thread and pass it around to processing some other data. So thread pools are something we want to avoid and use dedicated threads. I noticed some of the other competition is actually using thread pool based infrastructure to build their computations. And CPU pinning. I did some micro benchmarks and noticed that if you have 2 threads communicating, right, if you don't pin them, there was a approximately 20% hit in performance if you are not pinning them. So that was another idea that let's see what we can get if we pin these threads. Pinning threads, usually you have to do it when there are 2 threads are communicating, so that they don't move around, so that the CPU caches, stay warm. Memory model. This is actually a complicated topic. So basically, I realized you can sort of simplify it into 2 areas. One is basically reducing the GC pressure, and the way to do it is basically recycle objects. You don't go to the allocator to keep allocating new objects. And this is very critical in streaming because if you have threads, there's data always coming in. So every message is a new object. It's creating another object and sending it to another one, another thread, and that's doing the same thing. So the idea here is, if you can, as these messages are going through, if you can just recycle them, right? Just load them with new data, clear them, load them with new data, and send it back to the next downstream thread or something of that sort. So your GC cycles are going to be much less choppier, right? They're going to be much more flat. The second aspect to this was reducing CPU faults. And the way to do that is actually to control how your objects are laid out in memory. You kind of, typically in Java, when you allocate an array list, you get a contiguous set of memory, but each of it's just a references, right? Each reference is somewhere scattered in memory. So as you access the array list, it's kind of hitting all over the memory space. So what you want is, ideally, like those objects to be co-located so that CPU faults CPU faults are reduced, the cache faults, but particularly the L1 and L2 caches, or even L3. These low-level queues that we're using, behind the scenes, they do a lot of extra work to actually control how the data inside those queues is laid out. So they try to compact them in memory as much as possible. So the messaging architecture, so this is the current architecture. There's Michael Knowles' blog. He's done a nice job of actually documenting how the messaging works. So what happens here is, so this is basically the worker process. And just imagine there's only one Bolt instance running there. So the data comes in through the workers, whatever data is destined to this worker comes through this workers receive queue. This is actually the Bolt, the executor M of N, right? That's the Bolt. And what it's doing is it's got two queues internally, if you notice, the in queue and the out queue. So these are actually called the receive queue, and this is called the send queue, the out queue. And there's two threads there. So the first thread here, user logic, it's basically the whatever user logic you have in your bolts. So what it does is it reads the data from its incoming queue. It's called the receive queue. Does its computation and then emits it to the out queue. And then there's another thread which the user is not aware of, which is basically taking that from the local thread, from the user logic thread, and then sending it to another destination, which could be something within the process or could be outside the process. So what I'm going to show you is actually how this actually really looks like. This is a high-level view. So I'm going to zoom into this bolt. So first I'm going to look at this part, okay, the receive queue, and then it's the same stuff for the out queue. So one of the things we are using currently is called the disruptor queue. So we are using a queue called the LMAX disruptor. It's a very popular, somewhat popular concurrent queue. But we are planning to switch it out for another queue called JC Tools. And the reason behind is that primarily disruptor, it has good performance. JC Tools actually performs better than disruptor in my measurements, which you can actually find in the Jira. But the primary reason for switching out is actually that disruptor is way too complicated. Disruptor is one of the worst queues, in my opinion, ever designed. Okay, and the reason being that they've created one queue which serves like 20 different use cases. So normally if you're used to computer science, if I tell you how to use if I tell you here's a list, use it, you're going to look for two methods, right? Insert and remove. You will not find these methods in disruptor. What you'll find is you'll need to at least maybe there's 12 different classes you need to actually first understand before you use the class. There's barriers, there's ring buffers, there's strategies around this and that and everything. Like batching is a whole separate thing. There's consumers and all sorts of things. So JC Tools actually says, what we'll do is we'll create a separate queue for each use case. So they have you have one queue for a single producer, single consumer, a different one for multi-producer, multi-consumer, and so forth. So it's a very simple queue. It gives very good performance. It has batching also. So that's one of the things we're switching out. So let me just zoom in again as I was talking into this receive queue, right? And then show you actually how it works today and then what you're going to do about it to, in the new architecture. So this is what the receive queue looks like. So this is the same disruptor queue, and this is the user logic, right? When whoever the publisher, when he writes, he actually writes it into a batcher. So what's happening here is the publisher is not directly writing to the queue because they're trying to save on the synchronization operations. They're kind of grouping like a few items and then writing them in one go into the disruptor. Now it is possible that when this guy is writing some stuff, this is an array list, the current batch. He writes to the array list, and then every so often this fills up and then it gets flushed into the disruptor. Now it's possible that when you're trying to flush into the disruptor that the disruptor is full because the bolt is running slow for whatever reason. So there's an overflow, and that's so if you can't put it there, you put it into the overflow. But this is all happening in this black thread, right, in the publisher's thread. This is the blue thread, which is the user logic thread, which is draining the disruptor. And so there is another flusher thread, which is basically, whose job is to periodically check if there's some stuff here and push the data into the disruptor if possible. So there's like a timer-based. So then we have the send queue there. So this whole thing is just replicated as it is over there, right? So this is the guy. So the user logic writes it out into the send queue, and then the send queue has the same sort of stuff going on there. Finally, the send thread is what actually dispatches the data to wherever it belongs. It could go to another thread in the same process or to a remote process. So the send thread is actually quite complicated. So I've tried to show what's going on there. I see a lot of people cringing. But basically, it takes the data from the disruptor, puts it into an array list to sort of club it, and then it splits them into local versus remote. And then the local stuff goes into another array list. And in both cases, it creates hash tables, the local and the remote, basically keyed on the destination, right? So based on the destination ID, it will group all the messages. And then it's either handed to the outbound worker queue from where it goes outside the process, or it goes into another receive queue, just like this one. And that's how the cycle of message passing works with Storm today. So what we are doing about it now is basically saying we'll get rid of the send queue altogether, right? So once you remove that thing, this whole stuff goes. Then we are also saying we're going to eliminate this stuff here. Because of the existence of this thread, there was some synchronization that was happening between these two threads. So because if you remove this thread, that synchronization goes away. And we really don't want any locks in the picture. Actually, there is no locks here because this is a concurrent linked queue. Java has a linked list based queue, which is actually lock free, but it is a linked list. The problem here was that this is an unbounded queue, and it can just grow really long. So we actually want to stick with bounded queues so that process memory consumption is kind of not just, you just don't overflow it. So we eliminate that, we eliminate this, and what we have is something like this. So the publisher writes directly to the batcher, the batch, actually this shouldn't be disruptor, this should be JC tools queue. So the batcher writes to the JC tools, and then it's picked up by the executor thread, the blue thread, and then the blue thread just directly writes it to the local or the remote stuff and periodically flushes them out. So, so that's roughly how the new architecture looks. So I did some prototyping of this new architecture on top of Storm 2.0. And sort of this is kind of some of the preliminary numbers. These numbers are going to change as kind of we start getting more and more mature. It could get better, it could get worse. But essentially this is the 1.01 numbers. This is I had taken these numbers some time back. Basically the latency. So here I'm measuring how much time it takes for a spout to communicate with a bolt, right? You have one spout and one bolt. So essentially we get 3.4 milliseconds in 1.01. In 2.0 master, I'm seeing fluctuations every so often. At this time when I took the measurement, it was 7 milliseconds. And my changes had been applied on top of this version. But sometimes I've seen 3 milliseconds, sometimes I've seen 12. But right now it's still work in progress. So, but once we actually switched over to the simpler messaging model, it went down to microseconds, right? That was a huge leap in performance. So now it's interesting. Now you may ask, why is it interesting? Milliseconds versus microseconds. It's interesting if you're trying to build pipelines that fit within single-digit milliseconds. So if you have single-digit milliseconds between a spout and a bolt, then when you combine a few different bolts, then you easily go into double or triple-digit milliseconds with your total topology. So here the idea is if you go down to microseconds, you can potentially have microsecond latencies in your topology. I'm sorry, millisecond latencies in the cumulative topology. So these were very preliminary work. Okay, so then I also looked at throughput. Throughput without hacking, I noticed about, on the same one was 50% improvement. And without hacking, actually there was no change. So this actually was a big surprise to me that you can, your latencies have gone down dramatically, but why didn't the throughput increase? Basically, after doing a lot more assessment, I basically found out there was some bottlenecks elsewhere in the code. I've kind of given some estimates around, when I tried to kind of stub them out with some code, custom code, how the performance changed. So with some of the stuff, I could actually go up to 15 million per second. That was a huge improvement. But these still need to be addressed. They are not actually planned in this particular JIRA, but hopefully in 2.0 we'll be able to address some of these and get the higher numbers. So so basically there is room for improvement, and we know how to get there, and that's something we're going to be focused on. Okay, how are you doing on time? So 25 minutes. Okay, I have some time, so I'll also talk about the threading model changes. So in the threading model, this has to do a lot with the execution, how we structure the threads within Storm. So basically, the new model that kind of being considered is this. So we have the executor thread, right? The bolt that we talked about so far. It has its queue, which will be the JC tools queue. And so we're thinking that we can actually allow multiple spouts and bolts to actually operate within the same thread. So for example, if you have a spout emitting to a bolt, they may not necessarily have to be on the same, they don't necessarily have to be on different threads. The user may decide, in this case, I have only one instance of this, and it's a local shuffle grouping, so why bother with the inter-thread messaging? So we're considering allowing a spout and a bolt to be run on the same thread. And these tasks, these yellow boxes are basically user tasks. Then the grouper also we're thinking of turning it into a task. So in this case, there's no inter-thread messaging. They're just directly communicating either with simple array lists or direct simple method calls. So the task, the spout sends the data to the bolt either through an array list or a direct method call or something. And then the grouper basically will figure out where it should go. And then it goes to another bolt which is doing the same stuff. So there's basically this idea of a system task and a user task. User tasks are all the spouts and bolts. The system tasks are stuff that the system needs to put in place to get the glue stuff that the system needs to put in to get all of this working. So in this case right now, this is the inbound data, right? So this executor thread on the top left, it's actually taking in data from a different host that may be coming in and then feeding it there. So this is again factored into another executor thread and another task. So and then there's this on the bottom right, you see there's an executor thread for the outbound data. So it's all factored into simple executors and tasks, sort of a more normalized design. And potentially that means you can even control the concurrency on them. You can specify more of these or lesser of those or whatever, depending on the kind of I/O characteristics that you're observing. There's also some thought that we could do a special case messaging between two processes on the same box. So intra-host communication, right? You could do it through maybe shared memory-based kind of a messaging, so you don't have to go through the TCP layer. So there's a thought that maybe that also can be done in this model because you just plug in another one, another thread with a custom task, and that handles the intra-host messaging stuff. So that kind of so yeah, I forgot to mention. So then the shell process, right? It's doing very little. It's basically just starting and stopping these tasks, managing some of the metrics and reconfiguration and maybe heartbeats. So the outer shell process becomes very, very minimal. Everything gets factored into these executors and tasks. So I think that sort of concludes what I had to give an overview of. So I'll just open it up to questions and leave you with this link here if you're interested in looking into this further. There's a lot of opportunity to contribute if you're interested. So yeah. So question.
You didn't speak about how we handle backpressure in the new.
Oh, okay, good question.
Do you mind repeating the question for the
Yeah, sure. So the question was, how do you handle back pressure? So actually, the key to handling back pressure is eliminating this flusher threads. So what's happening is basically if any publisher is so what is back pressure? You're trying to throttle upstream, right? So what's happening here is if you can't write, this guy just retries. That's it. So currently, the model sort of which was borrowed from Huron, it goes and talks to Zookeeper and tries to throttle, sets flags there, and then everybody reads from there. So this is a much lightweight mechanism and back pressure where there's local back pressure which just bubbles up. So any component, right? If its input queues are choked, then that pressure just bubbles upstream because everybody starts retrying and it just cascades up. It doesn't put the brakes on the entire topology in one go. It's just sort of bubbling up. A kind of a mechanism.
What's the purpose of that array list for the local one? It's not in your next.
Yeah, I don't know why they had this. Actually, I was wondering myself. They could have just written it to the. Yeah, it's gone now. So yeah, so the question I guess was, sorry, I didn't repeat the question, is why do we have this array list here? It was not clear to me actually. Anybody else?
So what was the time difference again? When actually in throughput, when you were hacking versus not hacking? You said that was going to be a major area.
So actually, so hacking right now, what I've observed is actually the hacker bolt. There's an hacker bolt which handles the hacking. So there's some issues. I think it's just in the implementation. It's not a fundamental issue, but the hacker bolt today is kind of limited at around 2.5 million per second kind of a throughput in terms of how many acts it can process per second, and I think that can be easily broken. I think you can get several times more performance out of that. But here the reason you're not seeing a big change is because there's that bottleneck in the implementation that needs to be addressed. Does that answer your question? Yeah, so I don't think it's a fundamental problem in hacking itself because hacking is fairly lightweight actually. But in certain use cases, it's possible that you'll probably need more hackers or something if it becomes a bottleneck. Okay.
So the use of JC tools, were you using different queues in different use cases, or are you using I think you mentioned the wait-free bounded queue?
Sorry, say that again.
Which queue were you using in JC tools? Were they different?
Yes.
Trying to figure it out based upon the configuration?
So the question is, which of the JC tools queue was I using for this stuff? So JC queue, I think they have 4 major queues: multi-producer, single consumer, multi-producer, multi-consumer, single producer, single consumer, and single producer, multi-consumer. So by and large, we use the multi-producer, single consumer queue. There is one use case somewhere for a single producer, single consumer queue. The single producer, single consumer queue is wait free. The multi-producer, single consumer queue is lock free. So, yeah.
I guess my question was, are there any disadvantages? Because it cannot be good in all use cases, right? Would there be some trade-off that we have to think through this?
Well, actually, if you're in terms of performance, or so the performance of this stuff is so good that I think by the time we really reach the limits of its performance, that will be a long time away. But by and large, we are actually instantiating the right kind of a queue for the right purpose. So basically, we know exactly if this is a multi-producer or single consumer situation or not. So wherever there's by and large in Storm, because there's multiple spouts, that can write to a bolt or multiple bolts writing to a thing, it's pretty much almost always like a multi-producer, single consumer use case. So we always instantiate the right kind of there's logic there to actually check that and do the right stuff. So I don't believe we have some trade-off like that going on there, but I think even if we were to ever hit that, its performance is so high out there that we still have a long way to get there.
So what's your estimate for 2.0?
Oh, that's a secret. But okay, so he asked me what's my estimate performance for 2.0, right? So you can probably see some of that secret leaking out from here, right? My initial thought was maybe we can get to 10 million per second between 2 communicating instances right there. I have noticed that right now, if we can address some of these things, we should be maybe able to get to maybe 15 million per second. Can we go beyond it? That'll be nice, but definitely there is room to go beyond that. I don't know if we will or when we will, because I think Storm 2.0 will have some of the stuff, and then in the future releases, some of the other stuff will kick in.
Out of curiosity, when you run these tests, what is your base machine? I mean, how many cores?
Oh, this is my base machine. Yeah. So it's what, like a 4-core? Yeah, 16 gig 4-core. So I'm actually not looking. Most of my stuff is to really get quick numbers out. Usually, if I run it, maybe you'll get a couple million more or something on a better machine, but that's okay. Yeah.
Tuple is just a type.
Yeah, so this is a derived type from tuple, which is instantiated internally. So
Really, it's not a typo.
Yeah. This is the actual class type. So most of the tuples are actually instantiations of this by and large. So I'm actually so maybe we'll have a tuple impl 2 there right next time.
Yeah, that's an easy contribution for anybody who wants to contribute.
Yeah. Actually, these are stuff that's nicely. Yeah, you can take up things.
It will avoid a lot of future confusion. So think about it.
Any other questions or? Okay. So then I will pass it on to our next speaker, Karthik from Walmart Labs. I think we'll switch laptops here. Thanks, everybody. Oh, yeah.
So you have to clip this.
Okay.
Let's see if this works.
Is it on? Is it on?
Yeah. So you just take this direction.
Okay.
And then if you wouldn't mind repeating the question for the people
Sure.
on the live stream.
Sure, you do that.
Are we good? Hello? Hey, okay. Hey, good evening, everyone. I'm Karthik Devasigamani from Walmart Labs. I work in the product catalog team, which is responsible for building the product catalog for the entire Walmart e-commerce business. So in today's talk, I want to actually share with you guys how we leveraged Kafka, Storm, and microservices to build our product processing pipeline. So I want to start off by actually looking at how a typical customer experience at a retail store looks like. So let's say you're interested in buying a baby car seat. So what you end up doing is you go to the store. There's this booklet outside the store called product catalog, which none of us pick up. We just go into the store. We know what we want to buy. You keep looking for the section that says baby, and you go there. You look at all those aisles and look for baby car accessories, and then you find your car seat. You look at the brands. You go find the shelf that actually has the right brand, and you look at the price. You're able to touch the product. You're able to feel the product, and once you're happy, you pick it up. If you're not able to find the right product, then obviously you're going to take some help from the staff at the store. They'll be able to find the product for you if you're not able to find it. And yes, you proceed to the checkout, you pay, and then you leave. So, but actually, in order to make that seamless at the store, there's a lot of activities that actually go on behind the scenes. The store manager actually puts in a lot of effort to make sure that the different sections in the stores are organized correctly, and the product that you're looking for are actually shelved correctly. So that's a lot of work that actually goes in the background, right? And the next big aspect of retail is obviously big Black Friday and spike in traffic, right? So obviously you have to be prepared for it, because that's the day when you make the big bucks, and you don't want to you don't want your customers to have a bad experience on during those kind of times. So so this is a typical flow at a brick and mortar retail store, right? So let's see how this plays out in the online world, right? In the online world, you can't really go and touch a product or feel a product. So it becomes very important to have a catalog. So the catalog that you see at the store, right? The booklet, this becomes like the backbone in the online world. So you need a really good catalog. And what are the different pieces that actually contribute to a good catalog, right? So there are a bunch of functions that you have to apply on the raw data. The first one is normalization. Then you need to have a good taxonomy to classify your product. And then you have to match products. And then you have to shelve them accordingly on the website. And then attributes. Your products need to have the right attributes to describe them. It plays a significant role in when it comes to searching. And then grouping the products together. So I'll just go over these functions pretty quickly. So normalization is the process of standardizing on your input, right? So when you look at the raw data that flows into our systems, right? Like let's take this example of size, right? There are 96 different variations of size in production today. It starts from clothing size type, shoe size, rug size, baby size, whatnot, right? End of the day, all they're talking about is size. And so this is normalizing the attribute value, attribute name. And then the next normalization that we do is on the value itself, right? So the brand could be referred in multiple different ways, and each seller, when they send us this data, they could call it completely different from one another. And it's important for our systems to actually standardize on this and then operate in one way going forward. Here is an example of a brand name that can be spelled in multiple different ways. And it's important that when you're comparing products, you kind of normalize on all these things. The next one is classification, right? Classification and shelving kind of go hand in hand. Here's an example of a nail, right? So there are a bunch of variations of these, and it's important that you take this product and then find exactly what type of product it is. And you should have a standard taxonomy for it. And once you identify the product type, then it becomes easier for us to go and categorize it and put it in the right shelf so that users can actually go look for it and find what they want. So that's about that. And the next piece is attributes, right? So attributes, these attributes actually, there are some attributes that flow through the system where the sellers provide them, suppliers provide them. That's one aspect of it. The other aspect of it is derived attributes. So for example, if you take a product, there are a bunch of core attributes that are actually essential for us to display it correctly on the site, right? Title, brand, description, color, manufacturer part number, dimensions of the product, all of that. So in some cases, we don't get, let's say the brand color. So what we tend to do is we tend to look at the title, description, and we derive it from that. So we have attribute extraction models, which can actually go, given the title, figure out common things like brand. Typically, the title of a product has the brand. And condition of a product, that's another important thing. To know whether the product is new or refurbished. So all of that information typically is present in the title or description. And if it's not provided, you have to go extract them, because all these play a pretty significant role when it comes to showing the product on the site, right? And then this is a very interesting piece, product matching. So how do you compare products and say that they are the same? So the good thing is there are some standards around this. UPC, which is Universal Product Code, GTIN, which is Global Trade Identification Number, and then PLU, Product Lookup Code, and ISBN, and there are a whole bunch of other identifiers. But the unfortunate reality is this, right? These are not standard enough, and the standards are not enforced. So which means UPCs get reused, recycled. So there could be UPC collision. So the company that actually distributes GTINs is called GS1, and what they issue to a brand or a manufacturer is what is called as a company prefix. A GTIN is a 14-digit number, and what this means is if I'm PepsiCo, I could actually go and buy a company prefix for myself, which could be 1, 2, 3, 4, 5, 6, 7, 8. The last 6 digits is for me, and I could actually churn out 1 million products using those 6 digits, right? So, and the products that I churn out using those are something that I control, and I never tell this back to GS1. So which means nobody knows who owns this GTIN and what this GTIN actually belongs to. So even though these identifiers exist, you can't just go blindly by them. So that's where algorithms comes into play, right? So we have algorithms to actually go do comparisons given title, price, images, and a whole bunch of other attributes. So matching is done by a combination of both identifiers as well as algorithms. The next function of a catalog is grouping, right? This is a very essential element, because in order to make the customer experience much richer, right, where let's say you search for a pair of jeans, you don't want to actually see 7 different sizes and 10 different colors all on the same page. You want to see probably different brands of it, right? So this is a key element to your catalog. So that's called variant grouping. And the other aspect of grouping is bundles, right? Where products that are actually sold by themselves get packaged into one box and bundled, and probably you get a discount on the whole product, right? So that's grouping. So what are the different sources where you actually get data to build your catalog, right? So when you look at Walmart, right, we are into marketplace, and we partner with a lot of sellers, and we get data from them in the form of feeds, APIs, whatnot, right? And then we also partner with content providers to get content. The content could vary. Like there could be a partner who just gives us product reviews. There could be someone who just gives images. There could be someone who specializes in certain categories. So that's about content providers. Then there are suppliers / manufacturers of the product, right? So they come in, they upload their catalog, and we receive content from them. Then we have merchants who are basically merchants inside of Walmart who actually go buy products for the company that can be sold online. So their use case is typically around, go to a tool, enter the details of the product, and then it gets, and then it flows through the system. And then we have a whole bunch of, legacy catalogs that provide periodic updates to the catalog. So these are the sources, and then the goal was to actually go build a resilient, scalable, and robust data processing pipeline. What does that mean, actually, right? It means zero message loss. We don't want to lose any updates that actually go in through our system. This is very important, because any product updates that goes through the pipeline any product update that goes through the pipeline has to be processed no matter what, right? Either it's successfully processed or failure, but has to be processed. And then fault tolerance, right? Obviously, all of this is going to be running on a distributed system, and we want fault tolerance built in. If a node goes down, it should come back up, or the job gets moved somewhere else. So that's another characteristics that we wanted. Then when you look at all these different sources, right? Some of them are more important than the others. Like a merchant within the company, if his updates don't go through, it's slightly higher priority than a marketplace seller's content not making it to the site. So there's a certain degree of isolation that we require from the system. And then scale to millions of product updates per hour. Being in the marketplace, especially during holiday time, where it's important that we actually handle millions of product updates per hour, because the volume of traffic is just going to be insanely high. Then the next element was product updates in near real time. What this means is you make a change, you submit a feed to us, the change goes through the system, and at the end of it, it's actually live on the site, near real time. Then the other aspect that we wanted was traceability and checkpointing at various stages of the processing pipeline. So we kind of laid down these characteristics and then said, okay, how are we going to address this? How are we going to solve this? So we said, okay, there is this different, different sources of data that comes in, and we thought we would actually use Kafka as the data hub. So people can come in either through APIs or Excel uploads or feed submissions. All the data would just go sit in Kafka. That's great. How do you process them, right? Pretty straightforward, right? You need to have a real-time stream processing system. So we looked around, and then we kind of decided on Apache Storm, probably because a lot of us were from Yahoo, maybe, and the familiarity with it, and it was already running. It was kind of proven. Some of us in the team actually had experience, working on Apache Storm in the past, and yeah, it's proven to have it's proven that works in production and scales in production, right? And then in terms of database, Walmart Labs is pretty invested in Cassandra, and we went with Cassandra to store our catalog data. And as you know, NoSQL is just a key value pair, right? It's just a glorified hash map end of the day. So if you have to do secondary indexing and all of that, we needed something else, and that's where Elasticsearch came in. So Elasticsearch works as a secondary index for all the data that we have in our Cassandra. Okay, so this is great. So we decided on all of this, and now the question was, how do you implement your catalog functions that we discussed in the early part of this presentation, right? This was a pretty tricky choice, actually. So when you start writing a topology, right, it's very natural for us to actually take this data and then put each of those functions, like normalization, product matching, attribute extraction, all of that into a bolt. But then when we looked at it, we took a step back and saw this and said, you know what? Each of these are actually pretty core pieces by themselves. A normalization service, there's a lot to normalization, where we have something called Iron Bank, where all the attributes are listed, and then we have all these normalization rules that needs to get applied at runtime. And product matching, again, there's a whole bunch of algorithms that actually run there. So each of these catalog functions, right, they are pretty big, and there are about 2 to 3 engineers working on that. So now, if you actually make all of this into a single topology where everyone contributes, there's going to be chaos, right? You have to build a Uber jar. People are going to be checking in left, right, center, and yeah, soon there would be chaos. So we took a step back and, hey, you know what? And the other important factor was some of the programming language choices, right, were pretty natural. Like some teams that were relying on machine learning wanted to actually do their stuff in Python. And there were some folks in the team that preferred Scala. And there's some other services, some other teams, they wanted to actually build their stuff in Java. So we thought one way to kind of achieve all these goals and allow the teams to kind of operate independent of each other, we said we'll actually go the microservices route. And it was a pretty interesting choice, actually, and I'll go over the, how we achieved it and, what are the pitfalls and all of that, later in the presentation. So, when we decided to go the microservices route, one of the things that we were pretty conscious about was what is a contract between your Storm topology and the services. We had to have a very strict contract between the services and the topology itself. So the rules were kind of defined around HTTP response code, what each response code actually means. So we said here is the contract, go implement it, and then the teams kind of operated independent of each other, right? So, all right. So we went about writing our topologies, and the first question was, should all of this be in one topology, right? Then we took a step back and said, hey, let's break this down into 2 topologies. Logically, what this means is raw data that comes in, right, goes through a bunch of processes and gets saved as source data. When I say source data, think of it this way, right? There are 2 sellers trying to sell the same product. each of these sellers provide a set of attributes for that particular product. So all of this at the end of this topology gets saved as a seller's view of the product. So that's what this topology kind of tries to accomplish. So the data goes into Kafka. We pull it out through a Kafka spout. The first thing that actually happens is validation. We make sure that the data that's coming in is formatted rightly. We use JSON as the data format, and our model is it's a pretty canonical model that we use to represent our product. Once the data flows in, the first thing that happens is validate the data, and if everything looks fine, we write it into Cassandra saying that okay, this is good to go. We are ready to process this, and send it to the ACID and send it to the next bolt. The next bolt is kind of what we internally call as a composite bolt that does more than one function. Excuse me. It calls the normalization service, then followed by the classification service, attribute extraction, and product matching. So all of this happens in one bolt, and when a request goes to one of these services, you can think of it as the raw data that's going in and getting enriched in the process, right? So normalization would just add a whole bunch of, JSON would just take the input attributes, normalize them, and create a new normalized bag within the JSON that gets sent to the next service. The next service would actually take that input and then do whatever it's supposed to do. In this case, it would be to classify the product and determine the product type. So once that happens, then it goes to attribute extraction, which looks at all the normalized data and then tries to derive more attributes from the source. And then once all of that is done, then we go into the matching process, which tells you whether this product already exists in your catalog or not. If it already exists, then it's going to give an existing product identifier. If not, it's going to issue a new product identifier. Once that's done, then it goes into the grouping bolt, which essentially calls the grouping service and says, hey, group this seller's list of products. So what this means is if a seller has a red shirt and a blue shirt, both these would actually be grouped together on the source side. So once that is done, then it goes to the next bolt where again we validate our JSON data, make sure that everything is fine, and persist it as either error or process, depending on what happened in one of the services. So at that point, the first stage of our data processing is actually done, and the data is actually written to Kafka after persisting it in RDB. So from there, the second stage of processing begins. So this is where, from the seller's view of the data, we transform it to the product that is finally seen on the site. So first thing that happens here is, yes, you read the data from Kafka, goes through validation. Once everything looks fine, then we call a service called merge, which takes this incoming data, and then it has the existing data from our catalog and tries to merge this to form the final content that you actually see on the site. So once that is done, then the next service that gets called is shelving. So previously we determined the product type. So that information is actually used by this service to figure out where on the site taxonomy this product is going to be placed. So that is determined by shelf service. And once that's done, we run through faceting and attribute extraction again, which goes over each of these attributes to determine which of them are facets. And that information is again consumed by our search process. So once that is done, then we again push it to the next bolt, which is the product grouping service. So the grouping that happens here is not at the seller level, it's more at the product level. So what this means is if there is a seller A who has given you red and blue for the same t-shirt, and there is another seller who is actually given, say, purple and pink for the same t-shirt, all of these needs to be collapsed into one product so that you can actually show all the 4 colors to the customer. So that's what happens there. So the grouping happens there, and when things get emitted out from there are 2 tuples that actually gets 2 things that actually get emitted. One is the variant product itself. The second one is the the product group. The product group is nothing but it's just an abstract product which contains references to all the variations of that particular product. So the size of that payload is pretty big because there are products that actually have about 2,000 variations in production. So that payload can get really big. And what ended up happening was the publishing was actually submitting this piece of information to another system which was storing it and making it available on the site, right? Once we went live with this, that system was brought down to its knees because it was not able to handle the concurrency on our side. So the number of, because for every variant that goes through the pipeline, we were emitting a product group. And they were having problems handling that kind of traffic. So what we did was we said, we'll actually stop doing that. We needed to actually group them. So for example, if there are 100 variations of a product going through the pipeline, you just have to emit one update to the product group with all the 100. You don't have to update it every single time. So we wanted to do something called micro-batching. And Storm had a pretty well-established design pattern for micro-batching. So what we did was we pushed all the product grouping information to a separate Kafka topic. And the payload would look something like this. There's going to be a variant product, and there is a product group associated to it. So what we did was we put a router bolt in front of Kafka. All it does is just read everything and then sends it to the next bolt, which does field grouping. The field grouping is actually done on the product group ID. What this means is any update to a product group will end up going to the same bolt instance. So all these different product groups get converged there. And if you have 100 different variants for a given product group that goes through the pipeline, all of this will end up going to the same bolt instance, and that's where our micro-batching actually happens. We store this in a simple hash set, which kind of dedupes this. So even if you get 100 of them, finally you'll have only one in that. So micro-batching happens on both on two parameters here. One is the size. Once you reach, let's say, 50,000 messages, you can actually start processing them, or if you hit a time interval. So those are pretty configurable in our topology. So once it hits those thresholds, it'll start emitting them again. So this way, we kind of protected our downstream systems, which are not able to handle a very high volume of concurrent writes. So real-time processing systems and back pressure, you can't just separate them out, right? At some point, we all would have actually run into this, especially with the design that we had, where we had actually chosen microservices rather than implementing all of the logic in Bolt. At some point, you're going to have some service that will misbehave, just be slow, or take longer to respond, or is completely down, right? So what happens here, right? What is back pressure? If you're not able to keep up with the rate at which your upstream is actually producing, then you're going to have back pressure, right? And we were running in 0.9.3 in production. So depending on the kind of topology that you have, and depending on the the policy that you have, whether it's at least once or at most once, you're either going to end up with a message loss, or if you're doing at most once, you're going to end up in losing some messages. If you excuse me, if you are actually doing at least once, which is what we do, you'll end up in a scenario where the spout stops emitting after a certain point of time. So what are the knobs that you have to actually control this, right? So the knobs that we use in our system is, if we see considerable back pressure where one service is misbehaving or one of our database is having a hard time, few nodes down, then what we do is go and reduce the spout parallelism. This next one is Kafka message fetch size. The spout has a configuration that says how much of bytes to actually fetch from Kafka. You can throttle that down. The next one is max spout pending. I think before earlier to 1.x Storm, this was the way to kind of control the amount of traffic that you were actually going to let into your Storm topology. And then obviously you have a choice to increase your bold parallelism or your worker parallelism. But if your service is actually not doing well, increasing the parallelism is really not going to help. So you have to be mindful of that fact. The next thing is failures, right? It's going to happen all the time. And you have to make sure that you account for this and you design for this. So there are, at a very high level, when I look at failures, right, there are two types of failures that actually happen in our system, right? One is data errors, right? Bad data just coming in. And and those, you can actually put validations around it. Services have to handle it. So that's a fairly straightforward one. The second one is, given our microservices approach, there are going to be timeouts on services. A service is going to take longer to respond because the database that it's trying to look up against is slow. So you're going to have timeouts. So how do we handle timeouts, right? The timeouts are handled by, sporadic timeouts are actually handled by retries. So all our HTTP calls that we make are done using Hystrix library. So it's all asynchronous, non-blocking I/O calls, and each of those services, the calls that we make to the services have dedicated thread pools for it. The next thing is service outage, right? So there are times when your service is actually going to be down, and there is no point in actually keep on hitting those services when they're already down, right? It's only going to compound the problem. So Hystrix has a circuit breaker built in, and we've configured it in such a way that after X number of calls start timing out or X number of errors from the service, we'll actually open the we'll start opening the short circuit, and that service would actually get we'll just bypass the service. And if there are any other services in the pipeline that actually depends on that, then it's going to end up as error, and our validation would catch it, would get logged as errors and get saved into our Cassandra database. And then the next class of errors is actually fatal errors, right? So this is where it gets very tricky. When remember, I talked about checkpointing at different stages, right? If you're not able to persist your data, to me it sounds like doesn't matter whether you process it successfully all the way. It's a failure. You can't persist it. So there is no point in moving further. You can't really do anything more with that. Even though you have processed it successfully, if you can't save it, there is nothing more you can actually do. There's no point in processing any further messages. So the approach that we took was any database write errors, right, where we are not able to persist it. If that stage fails, that's like a fatal error for us. And at that point, we actually fail the tuple. And when we fail the tuple, it goes back to the spout, and the spout actually starts replaying that tuple until it actually succeeds. So if your database is down for 3 hours, you're just going to be there churning on this. Until somebody goes and fixes your database, you're not going to move forward. All your messages are not lost. It's all sitting in Kafka. So we're just going to churn, just keep spinning on the pipeline until the database issue is actually resolved. So this ensures that you don't lose any messages, which was one of the top priorities when we actually went about designing the system. So how did we do on our all the characteristics that we wanted, right? So yes, we were able to get 0 message loss, and this has been running in production for about 2 years now, and I haven't heard a single issue where where we've had message loss. So the way we achieve that is by actually anchoring tuples and failing tuples so that it goes back to the spout and gets replayed, right? And we've set that constant to max offset behind to actually long.max. So that's how we actually achieve 0 message loss. The next thing is product updates in near real time. So once it comes in, goes out, it's out there on the site. The next thing was priority queues, right? We wanted to kind of provide a higher importance to some of the sources. The way we achieved that is actually through a combination of partitions and topics. So when we started out, we said, Walmart-owned items, which is called 1P, would actually have higher priority. So which means we would have dedicated partitions in Kafka where all the 1P products would actually go. All the 3P, the marketplace items, they would go into a separate set of partitions. The producer would actually guarantee this. So once this happens, then there was some sort of partitioning. So if there are a lot of traffic from 3P, it doesn't really impact the 1P products and vice versa, right? And then as we started scaling out, we went to this approach of saying, just deploy them separately, have 2 instances and topic-based isolation. That's where we kind of ended up with. The next one was scaling to 1 million, millions of product updates in an hour. We were able to do that with Storm. And then fault tolerance, right? If any of the node goes down, we didn't have to do anything. Storm would just, if the worker goes down, then Storm would actually, move all the tasks that are actually running there to a different machine. And if a node goes down, same thing. And Nimbus and supervisors are pretty stateless and they fail fast. So if they go down, if you bring them back through a monitored process or something, it's just going to come back as though nothing really happened. And then checkpoint. So the way we do checkpoint is, if you look at our topologies, we were actually persisting the state at different stages. And so that's kind of our checkpointing at different stages. Cool. So then the next part is, what do we monitor, right? When you're actually building a system that's actually powering your product catalog, it's pretty important to actually monitor things, right? And the things that we monitor, is the very first thing is the Kafka lag. Kafka lag is basically an indication of the amount of traffic that's actually coming into your Kafka and the rate at which you actually consume. It kind of gives you the delta of that. So I think we use Kafka Mon. I'll cover that in the next slide. So lag is one thing that we actually measure. The second one is the bolt capacity. This is provided by Storm, on its UI. That's a very significant metric to actually monitor what is going on, right? Once your capacity starts shooting up above 5, you have a problem somewhere in your topology, right? So that's one thing that we closely monitor. The next thing is the JVM, standard JVM heaps, threads, all of that. And since we are based, the whole topology is calling a whole bunch of services at different points. So it's very important that we continuously monitor our service SLAs and make it a point that to tell the service owners that, hey, you know what, there are these many number of service SLA violations. Go take a look at it. So that's one. We also like I said, we use at least once processing semantics, right? So tuples are going to fail, and this is something that we again monitor separately on our side. The Storm UI also provides these numbers, so that's pretty useful as well. The next one is system errors and data errors. And all of this gets recorded into our database, and we have Elasticsearch to query and find out how many data errors and how many system errors we have. And then the usual OS metrics like CPU, load, memory, all the basic OS metrics, right? So what do we use for monitoring, right? Kafka Mon, pretty useful. It goes, figures out where the latest offset is on Kafka, and looks at the current, current offset that was processed on by your Kafka spout. Does it delta between the two, and that is your that's your lag. So that's one thing that gets monitored by our operations team, engineering teams. We have alerting around it. So that's a pretty big indicator of what is actually going on in our pipeline. The next one is Guano. This is a tool that I actually just love this. I don't know who wrote it, but just love this tool. This makes it very simple to actually go and replay. It's very easy to say that, hey, you know what, if you messed up, you can always go back and reprocess. But how many of us actually do this in a very easy way, right? So Guano is a tool that actually allows you to take a snapshot of Zookeeper directory. So now when all the state of your Kafka spout is actually saved into Zookeeper. So all you have to do is go take a snapshot of, pause your pipeline, take a snapshot of your Zookeeper state, and export it to a directory, deploy your code, make sure everything is working fine. If things are fine, great. If things are not fine, then you may want to actually revert to the previous version of your topology and go back and reprocess everything. At which point, after you redeploy, you import back the last saved state into Zookeeper and then start your topology again. You're basically replaying from where you left. So that's a pretty important toolkit to actually have. The next one is Storm UI. Storm UI, especially with 1.0, the log viewer and all, it's pretty awesome. And we have the typical ELK stack to actually go and search through our logs and all of that. Then we use Grafana to monitor our service latencies, and so the other system that we have for our monitoring is Druid. We actually collect analytics and tracking metrics for all the data that goes into our Kafka topics. So we take that information and put it in Druid, and it gives you a pretty good picture of how much of data actually flew through our system and what actually happened, where it failed, and all of that. So we use that for tracking and analytics purpose. Fault injection tool. This is something that we actually built, in-house, and this is along the lines of Chaos Monkey that Netflix has. So it's able to inject, faults at different points in the system and make sure that things are actually coming back. So you can actually go bring down a supervisor and make sure that everything is back up. A service, you can actually kill a service and make sure that it comes back automatically. So this is our cluster that we use in production. We have HA Nimbus, 7 supervisors, 320 cores, 2 terabytes of RAM, 35 slots, 14 topologies running on this, approximately 6,500 executors, and we process around 150 million Kafka messages per day, and 360 million network I/O calls. So this is the cluster that actually powers our entire product catalog. We have another cluster that actually is used purely for audit and tracking purposes, the Druid application that I was talking about. We've kind of kept them as 2 separate clusters at this point. This has a single Nimbus, 5 supervisors, 160 core, 1 terabytes RAM, 155 slots, 94 topologies. That's 1 for every Kafka topic that we want to actually monitor and track, right? And then about 1,400 executors, and it processes about 1 billion plus Kafka messages every day. So this is a pretty important thing in period in e-commerce, holiday season, right? You don't want to lose business. So there is a lot of planning that actually goes into preparing for holidays, making sure that all the systems are stable. They're able to take in the additional traffic that comes in during this time, right? So one of the things that actually happened for us was our marketplace platform really took off. We had around 100 odd sellers on our platform, but from the beginning of last year till the end of last year, we had tremendous growth there, from a few hundreds to few thousand sellers, and we had over 100 million seller SKUs. And this is the interesting part, right? When you go into holiday capacity planning meetings and all, because of the rate at which our business was going, nobody wanted to take a chance. They were just throwing in numbers saying we expect 3x, 4x, 10x, just go scale it. So nobody had a really good hold on how much traffic to actually expect. So that made it really challenging for us, right? Not knowing. So we kind of tried to be ahead of the game, where in August of last year, when the moment 1.0.2 was actually launched, the first thing that the team did was huddle back and look at 1.0.2 and said, hey, you know what? We want to actually go there. That's the first thing that we did. We did that in around August, September, early September, and it came with HA Nimbus, improved performance, improved back pressure handling. I mean, that improved back pressure handling made a big difference, at least to my lifestyle, where I didn't have to wake up all night and troubleshoot some production issues. So thanks to the community for that. And then sometimes some of these performance problems, right? The most important way to look at it is not get lost in numbers and scale, right? You have to measure things. The interesting thing that we did here was we just questioned ourselves. why are we getting 6x traffic? Why would sellers actually go update their catalog so many times, right? Why are they updating their titles so many times? We went and looked back. It turned out that most of the times the sellers actually change. Let's say a seller has a catalog of 100K. He would just change the title for one product, and he has this habit of uploading the entire Excel sheet. So there are 99,000 odd products that have absolutely no change, just one product that changed. And we were just processing this as though something changed. So what we did was we implemented change detection, and the moment we did that, like 70% of the traffic was just noise. Everything that came in that got processed successfully previously, we said we're not going to reprocess this again. So that made a big difference to how we actually handle our holidays. The next thing was we started cranking up on our monitoring. Started doing periodic fault injection tests, and then we kind of separated out, redeployed our topology for 1P versus 3P, so that both these things don't run into each other. Lessons learned: things will fail, for sure, and it'll happen when you go on long weekends, when your kid has a birthday party, and when you least expect it. When you're playing a cricket game on a Sunday. So yes, so things will fail. So be prepared for it. Monitor everything, right? It's very important that everything gets monitored. This is one piece where it's very hard to say what are the pieces that we want to monitor upfront. So this is something that you'll actually learn as you go. The next thing is automation, right? When things fail, try to automate. If a supervisor dies, automate bringing it up. No point in actually having a person kind of do this again. Last minute.
No, that was not.
Oh, okay.
It was a joke about automation.
Oh, okay. So yeah, automate everything. And scale is not a feature, right? As the business started growing, one of the things was, hey, 2 sprints, can you just scale this 3x, 4x? That's not how scaling works, right? You got to factor scale at every aspect of your development. Any feature that you build, think about what's going to happen, right? Is it going to help scale your system better or not, right? So scaling is not something that you'll get in a sprint or 2, okay? Storm works well with large payloads. This is a significant learning personally for me, because in my previous experience with Storm, we were actually playing around with small payloads which are order of few bytes or maximum 1K. But here, some of the use cases that we have, the product payload is around especially the grouping one is around few MBs actually, 5 MBs to 8 MBs. It's insane. So Storm does really well with that. Next thing, logs don't lie. So don't trust what people say. Go to logs. Okay. Especially with our architecture, right? There are so many services involved. People are going to claim that, yeah, I'm doing fine, but when you look at the logs, it doesn't really add up. So go by the logs. Logs don't lie. And then microservices, with all the independence and everything that it provides, teams can operate independently. It comes at a cost. And I believe you have to find the right balance when it comes to microservices. So running out of time, so I'll quickly wrap this up. So going forward, right? What are we looking for, in our roadmap? Stateful stream processing. This is something that we really want to explore. We've been doing. We kind of manage our own state today, and when we looked at Storm 1.1.0, 3 things that actually caught my attention and something that I really wanted to play with: streaming SQL, Druid integration. We do Druid integration today in a completely different way. And then PMML, I think this was touched upon today as well. And finally, this is the team that actually built the whole thing. So yes, we are hiring. If you're interested, there's a link there, or feel free to reach out. Thanks, everyone. Do we have time for questions, or any questions? Yes.
So is your cluster the sort of OpenStack cluster on data center?
The cluster that we have is on bare metal, not on OpenStack.
Could you repeat the question?
Oh, sorry.
Could you repeat the question for the online folks?
I have 2 parts.
Okay.
First part is that OpenStack.
Oh, can you use?
Whether it is or it's not. What kind of cluster management tool you are using. And the other question is, looks like you are using Elasticsearch cluster, right? For data lake, between HDFS and Elasticsearch, which one is better for data lake, typical enterprise data lake?
Sorry, what was, I didn't get the second part of the question. Data lake?
The data lake.
Uh-huh.
You know, HDFS can be used for data lake. But you guys are definitely, for indexing or these kind of, are using Elasticsearch, right? Elasticsearch cluster can also use for data lake. Yeah?
Okay. So so the answer to the first question is, we actually have built in-house tools that actually go do the automation for deployments and all. So all of these are done on bare metal. So Walmart has what we call internally as packs to deploy all of these things. But since we are running on bare metal, that is not supported. So we've actually built our own tools for doing that. The second question is, Elasticsearch. What?
Elasticsearch and HDFS. What do you think? Which is better for data lake? Yeah.
So from the use case for Elasticsearch on our side, right? It's more of a secondary index for the product data. And I don't know how HDFS would actually fit there. So Elasticsearch is primarily to act as a secondary index for our product data. So, yeah.
Okay, so when you mentioned microservices, you basically had number of things happening on a single board instead of having separate boards.
Yes.
What was the reason, and how did microservices really got implemented? That seems like something proprietary.
Oh no, it's just a sorry. The question was around microservices, how microservices are actually implemented, and why a bolt actually was calling more than one service, right? So, so I'll answer the second part of it. So we don't have any strict guidelines as to how a microservice needs to be built or anything. We don't have a standard platform. It's up to the teams. Like I said, right? That's the freedom that we got with microservices. People can actually go build stuff on. So we have some services that are on Scalatra and Scala, and we have services that were on running on Python, and we have some on Java, Tomcat versus there are other flavors of it. So it's the interface is yes standard HTTP. Yeah, and the other part of the question, why did we actually use a composite bolt? So the way we looked at it was all those 4 or 3 different functionalities has to be done together. So we kind of felt that just putting them all in one bowl kind of made sense. So that's the rationale behind it. Yeah.
My question is about the size of the messages you mentioned.
Mm-hmm.
So you said they could span over 1 megabyte. I know
Yes.
that the default maximum for Kafka is 1 megabyte.
Yes.
Have you had any issues
Yes.
having it increased beyond that limit?
Yeah. So the question was about what is the maximum size of your messages on Kafka. So here is what actually happens, right? If you go back and look at this, we take the data from Kafka and then enrich it, right? So by the time it actually starts here, actually this is the source, right? By the time it starts here, it's actually few Ks, like 10K to 20K. By the time it gets processed and enriched, all the way there, at the end of the pipeline, that's where it actually becomes few M. So we do have, we have actually increased our the max message size in Kafka to actually handle this. And we do have regular trouble when we try to write such a big payload in Cassandra, we get timeouts all the time. So yes, so we are actually pushing back on our product team to see, does it really make sense to have such a big product group with 2,000 variations? So yeah.
How do you guarantee the data compatibility between the services that you have? Are you using schema registry for your data or something like that?
So good question. So we are getting burned because we don't use that today. So that's something that I'm looking forward to the next talk on. Oh, sorry. So the question was about, do we use schema registry or something? How do we manage the data in Kafka? So today we don't use it, and we are burned because of it. And I'm really looking forward to the next talk on schema registry and all of that. So yes.
Guaranteed message processing you are implementing, right? But your processes are pretty big, so the whole chain is pretty big. You cannot predict for a given message how much time it takes to process it. So
Yes.
how are you handling that?
Yes, good question. So this is something that comes by practice. Oh, sorry. Okay. So the question was, how do you know how long your tuple is actually going to take, right? In a nutshell. So the answer is yes, practice. We tried some settings, the 4 knobs that I actually showed here. So that's what we play with all the time. We play with those, we tweak them repeatedly. We fail sometimes, we get it right the next time. But once it kind of once you find the sweet spot, kind of settles down there. So practice. There's no magic bullet for it, I guess. Yeah.
Wait. How
Okay.
How does that change the latency?
So we actually add services. So sometimes what really happens is each of these services, right, can take longer. So which means the overall latency of your processing on the topology can increase, right? So once that increases beyond a certain point, your spouts are actually going to start failing after timeouts, and which will again cause things to spin in the pipeline. So it's a fine balance that we sort of try to accomplish that. And yes.
I don't get it, but so what you're saying is that you're increasing the number of microservices that are bound to your instances, your vault instances, so that you don't back it up so much?
No, not that. So what I was trying to say is the number of the amount of time that it actually takes for a tuple to actually get processed, right? It depends on all these services and how long it actually takes for each of them, right? So the way we kind of configure all our tuple timeouts and all these things, right? All of this is dependent on that. So using these knobs, what we try to accomplish is arrive at a sweet spot where tuples don't time out, right? So that's kind of what I was alluding to. Hope that answered your question, but we can take it offline.
Yeah, we should.
Yeah.
That's
Sure.
I
Okay.
understand. Thank you.
Yeah.
That work? I can speak loud.
Yeah, this is for the live stream and the video.
Okay, so can you say something about auto scaling? What kind of peak data size and off-peak data size do you have daily? And the peak your cluster size, off-peak cluster size, as well as what kind of storage architecture do you have? Right?
So machine configuration, the bare metals that we.
1 million topics per day, right? Kafka topic. In terms of data size, what kind of data size do you have?
Yes. So I don't remember them on top of my head. Actually, I can maybe I can get back to you offline. I don't remember. We have about. Oh yeah. Okay.
I'm part of the team. So essentially, the way Walmart runs is we have our own private cloud on top of OpenStack. So just like what Amazon does, one can choose different flavors, either an XL or a large or a small. So based on the instance types, you get the cores and the memory. Typically, the microservices that he was referring to, they normally use large size because the idea being that you want to have horizontal scaling, so have more instances of it as opposed to go XL, which will be more cores and more memory. So that's how individual teams decide based on what they need. Either a large or an XL is what I've seen mostly in a production environment.
So auto scaling, you're using OpenStack feature.
Exactly. So we have our own, we don't run OpenStack as is. We have a forked version of OpenStack, and we have built our own tooling on top of it. So that's how we manage the
So the
orders.
typical machine, direct attached storage, what kind of size of machine per VM do you have?
The storage is essentially the same as what AWS. It's all based on what you need, right? So most of the people will either take an ephemeral or they would go and take a block storage.
Okay.
Yeah.
Thank you.
Hey, I thought Suresh did a good job of making you stay back. Thanks for your patience, guys. I'm Sri Harsha. I work at Hortonworks as a lead for the stream processing team. So we are at hard at work for past 8 months or so, building Stream Analytics Manager as well as registry. and we are really excited about presenting it today. I'll try to skim some of the slides. I want to focus more on the demo, so that kind of gives you much more idea about what we are trying to do. So a little bit of history of streaming at Hortonworks. So we started off shipping a Storm back in 2013, late 2013, and initially, also started shipping Apache Kafka very early on. Before anyone started, we already recognized the importance of Kafka as the enabler of streaming applications. So continue to drive innovations in Storm, as well as participating a lot into Apache Kafka, added security features as well there. So last 3 years, we did, talked to a lot of users through community, as well as our customers, sat with them through the support issues, sat with them analyzing their use cases. This enabled us a lot of learnings. All of these learnings actually drive us developing registry as well as Stream Analytics Manager. I'm going to refer that as SAM so that it won't be long. So that's pretty much all our motivation, all our use cases, all our learnings got into these registry projects and SAM as well. So I'm going to talk about registry. So when we look at registry project, we are not just talking about schema registry per se. We are looking at the entire central metadata repository. That is your schema. It could be your ML models. It could be your service for other application to discover, as well as application configuration that you want to store. So when we are building the initial set of features, we've started building a foundational framework around registry, such that other developers or ourselves can build additional registry services such as ML and so on. So initially we developed schema registry along with this framework. It took us like 2 to 3 months in between, and then we started adding ML registry, which took us 2 weeks. The foundational frameworks will give you REST APIs, UI. At the core of it is a version entity. So pretty much any registry service that you want to develop, you want to version your schemas, you want to version your models and whatnot. So that all is taken care of by the foundational framework itself. So that will enable you to kind of quickly add any registry services that you want to do. And also modular approach of running these services. That is, as a user, you might be interested in just the schema registry. You can just spin that up in the server, or you want to combine with schema registry as an ML registry as well. So you can combine, choose on which way you want to go, so that operationally you don't want to run one service there and one other service here. So it's make it easier for you to run it as well. So right now we have schema registry and ML registry done. So a little bit more about the schema registry. A schema registry is nothing but a shared repository of the schemas that will enable you to kind of define your schemas of streaming data. Like typically in Kafka or any Kinesis, anything, it's storing a byte payload, right? So nobody has any clue about, people has a clue about it, but the message itself is not carrying any schema about it. So on the side, on the stream processing side, what you traditionally used to do is take that byte buffer, convert that into JSON, and probably code it up saying that JSON.getDic, dictionary, first name, last name, and so on. So on the producer side, if someone wants to change or evolve the schema, add 2 more new fields, the topology has to adapt to that schema, saying that redo the code, redeploy the topology or whatnot. So we want to kind of avoid this setup, this communication between producers and consumers, and independently they can evolve the schemas without the consumer has to kind of go through this pain. So, and also kind of discoverability and collaboration across your organization as well. Once, as let's say you are a weblog team, you're publishing your data into Kafka, there are a myriad of teams that want to use that, and they want to understand what is the format of this data that is getting into Kafka. They can come to the schema registry and discover all the pieces of information. So a little bit of nomenclature about the schema registry is schema group. Again, with the schema registry, we are not just targeting just for Kafka needs. We want to address all the needs like HDFS, Kinesis, or different messaging queues. So schema group is a logical entity that says, okay, you're probably using Kafka schemas. You want to group them as a single group entity. You can define the group as Kafka, or HDFS, Kinesis, and so on. Schema metadata kind of defines name, description, what this schema about, so that another user can find it and understand it. Schema version is where you actually put the text in, if it is Avro or protobuf or not. So this is kind of how the architecture kind of looks like, or the integration points. So let's say you have a producer and consumer. Think of producer and consumer as not just Kafka centric, but in general, anyone producing data into any message store, or anyone who is trying to read the data from that message store. So what we are trying to do here is, especially in Kafka specific case, you have a producer running, you have a serializer interface. We ship schema registry client that can talk to our REST APIs. And as a producer, you will give either schema text or use an existing schema that someone else registered, saying that I'm producing a type of data that's going to adhere to this particular schema. So schema registry client will make to registry server. If it finds a schema, it will use that by fingerprint matching. If it's not, it's going to create a new schema for it and start producing data into message store. So each message ID, each message that's going into your queues or HDFS whatnot will have a header of 8 bytes that contains ID and version that is uniquely defines what is this particular byte payload is about. So on the consumer side, when it's actually reading it, it's going to hand over this byte array to your deserializer, which looks at your first 8 bytes, figures out what is the ID and version, and makes a call to schema registry, figures out that, okay, there is a schema that is there. I'm going to take that, I'm going to deserialize according to that particular ID and version. What is this enabling you to do is, on the producer side, I might have a slide like this. On the producer side, you can independently evolve irrespective of what consumer is running again. So let's say if you have a schema that says first name and last name, let's say that is running on V1, and consumer is already reading that, and you want to add address field. You went ahead and added. Whenever you add a new field, new version is created, and you can get to define what is the compatibility policy of this schema. It is backward, forward, full, or none. If it is backward, your older consumer running on an older version still continue to run even if there is new data that is being produced. And any consumer that is running coming up can actually figure out the new schemas because you are associating a small byte into the messages, defining what is the metadata about that particular byte, particular message rather. So that is in a nutshell what's how the kind of interaction going through. So as I said, we have a compatibility policy. When you're actually registering the first time the schema, we're going to ask for what is the compatibility policy that you want to set to. So if you set backward, any further updates to this schema will enforce that rule. So if you, let's say, define first name and last name, and the new version you try to take and set the compatibility policy to backward, and in new version you try to delete last name, we're going to throw an error saying that you set a compatibility policy to backward, you can't delete this. And all the schema versions are immutable. So once you register that, you cannot delete it, so that any consumer who is running doesn't get accidental delete and doesn't go and throw away in a production environment. So another thing we are kind of focusing on is right now we build registry based on Avro. Avro has a nice compatibility policies and everything, but we do recognize the need that not all of the users will end up using Avro as their format. So what we are trying to do here is like allowing user to define their own type. It could be protobuf, JSON. We also have a converter policies which allows you to convert from CSV XML into Avro or whatever the type you choose to be. So type is kind of defined by the user itself. If they choose to use Avro, that's great. If they're not, they can get to choose anything. So in that cases, not all of them will have a good evolution story about schema. So what we allow you to do is write your own serializer and deserializers of that particular type. So you register an XML, you have a particular way of reading that data, so you can supply a serializer and deserializer and register that into the schema registry. So during the runtime on the schema registry client, we'll pull that serializers and deserializers, load it into an isolated class loader, and deserializers depending on where you're running it. So this will allow you to not just stick to Avro, but define your own policy, define your own type in itself. Since schemas are immutable, so we don't need to make a lot of calls into REST API of registry server itself. We can highly cache the schemas on the client side, so that allows you to scale better. And we do have an HA also. So all the calls goes to leader, similar HA story in general, how you find out in many of these cases. So we already have, as part of this project, a Kafka integration. NIFI, if you know, that is another flow management system that's also got in Streamline, or SAM that I'm going to demo next, is also heavily used into schema registry. So again, we have a nice UI as well, so we are evolving that as we go along. So future things that we are currently working on, security, of course. Security kind of goes much more deeper than authentication. For example, you have in a schema something called as lat long, a subschema, and you want to put restrictions against who can use this subschema against it. So you can enforce a policy, like let's say money, for example, that's a record, and you don't want to kind of expose that to everyone else. So you can put restrictions on subsections of a schema. And audit of schemas and clients, for example, you deployed this in a large cluster, you have multiple groups coming in and using it, and you want to know which are the clients using this particular schema. So we have an heartbeat mechanism that can go and register their usages with us, and we can display on the UI itself. Rich types in schema definition, again, Avro gives you primitive types. What we want to get to kind of give a hints capability, saying that, hey, this is a user ID, is a unique ID, so that on the application side, you can do much more interesting things, as well as latitude and longitude combined be a location, so you kind of format or process it differently. So a lot more richer integration into your schema definitions. Pluggable listeners, again, schemas right now, there are multiple metastores that are going around, like HMS, high metastore or whatnot. If you want to centralize that, that's where we're coming in with the pluggable listeners. You can install that. You're going to pull in all the different schemas that you have in your cluster into central repository. Schema policies, again, if you have this in a production, you don't want anyone come in and register a schema, make this available in a production cluster. What we are trying to do here is kind of a peer review kind of thingy. You publish your schema, it goes to a review process, everything says the users who are trying to use the schema kind of goes through that and goes through kind of a typical code review process kind of thingy, and then allows you to publish the schema to be usable by everyone else. And notifications, again, as a consumer of the schema, you started using V1 version of it, and you want to subscribe to any changes that's happening to it. So we allow users to subscribe to it, and whenever there is a change, register a new version, you get a notification sync. And lastly, converters, again, there are different types of data that is going through comma separator, CSV, XML, whatnot, but there is Avro, protobuf are much more well-known types. You want to convert that existing CSVs into that one. So converters will allow you to do that. So it's a pluggable converter mechanisms. Once you register that, we will allow you to do it for automatically on the fly. So that's our future roadmap with the registry, what we have and what we're currently working on. More importantly, it's an open source, Apache 2.0 license. We are working on our Apache incubation proposal as well, and already seeing good amount of interest from outside community. And obviously, we want to welcome anyone who are interested in this to start coming to us and contribute. So that's about registry. Take some water. If I want to have any quick questions, I can address right now.
Thanks for the presentation. I know that there is a schema registry made by Confluent. And what is the difference, or maybe what is the best feature, the better feature that you give in this project?
Yeah, so we are looking at a more larger picture of repository or registry use cases. The first thing is allowing users to kind of not just look at schema registry itself, but ML registry and other projects as well as a central metadata repository. And we are trying to integrate into multiple projects, not just around just Kafka. That's more particular in Confluent schema registry. So you can actually, I can show you in demo, you can register a schema for a HDFS directory and use that schema to kind of process within your stream processing application. Not just that, and also type. We're not just sticking to Avro. Our plans is just beyond Avro, because we do recognize that not everyone wants to use Avro. And also, pluggable serializers and deserializers with Confluent schema registry, which talks to Avro. They expect you to use Avro serialization, which expected, of course. But we wanted to evolve beyond that, and basically enable other types, serializers. For example, especially in NiFi use cases, what they have is a flow file, which is a huge file that they have. So they don't want to give the entire file to the serializers and wait for it to kind of go through that process. What we have is a snapshot pull based, which will allow you to kind of define a boundary conditions, saying that whenever you see this delimiter, that's my record in this huge file. So we immediately return back. So it's like an event-based deserializers, event-based serializers kind of thing. So not just that, in the end, like a feature enhancement that I talked about, those are things that we want to evolve beyond what we have in the schema registry. Again, we talked a lot of users, especially mirroring capability that we are adding right now, which is, you have 2-3 clusters. You don't want one schema registry instance serving all these clusters and all these different regions. So you can install schema registry independently in different clusters, and we will sync whenever you do updates across all these things. So that will allow you to scale much better and not have cross-colo issues and stuff. So before answering, I'm going to go quickly into Stream Analytics Manager. That's our heart and soul poured into it. So again, by shipping Storm for 3 years, we learned a lot from users about what is a stream processing application in their view, what it takes to build a stream processing application, how do they monitor in production, and what is they are actually doing with that application, that is storing the data, viewing the data, how the analytics of their stream application is working. So our goal is to make this easier for the users, not to kind of fiddle around, hey, there are better APIs, better engines. Instead, we want to concentrate on actually providing a better UI editor that allows them to develop this application quicker, and also make them concentrate on their business use case rather than kind of fiddle around how my Kafka integration working, how my Hive Bolt is working, or whatnot. So that's where we want to get away and make the focus around the business use case that they are trying to solve. And other aspect of it, like once you build the application, you pushed into production, like Karthik talked about how they are monitoring the application. So we want to address those use cases. How do you address the lag of a Kafka? How do you, address the failed events that are happening? How do you debug this application? And once this is addressed, what is actually you are doing with the data that you are processing? How are you deriving the insights into it? How are you helping your business itself with this application? So combine all these together. We want to build a one-stop solution rather, in the sense that you come to here, you get to have all these capabilities within one application rather than installing myriad of different services to get to what you want trying to build. So that is our guiding principle. Again, as I said, there are streaming engines pretty much every other week, I guess. There are multiple APIs. Everyone says the word count topology can be replicated much more quickly. But in reality, as again we've seen in Karthik, it's a lot more complicated than a word count topology. So a typical application could be looking like reading from Kafka and doing some kind of processing, looking up some tables in databases, or generating some data into your HBase or Hive tables. So how do you make this easier, the interaction of these external services easier? And again, anyone who deployed a topology using Storm, or any other engine for that matter, if you're integrating with HDFS, HBase, you need to package all your configuration files. You need to figure out where the brokers are running and all that stuff. So how do you make that easier? And once that's done, how do you make operations and monitoring this application is better, and also debugging easier? So that's where we want to kind of address. So the way we are looking at is kind of 3 personas. There is the application developer itself. How do you address their needs? We have a topology editor, a graphical topology editor. I'm going to do a demo that's probably easier to explain there. And also address the needs of DevOps. How do you monitor? How do you kind of enforce alerts and stuff like that? And finally, Stream Insight module kind of addresses your analytics needs. So underneath it, there is a unified streaming API. So again, we don't want to kind of get into is Storm better or Flink better or which use case is better or whatnot. Instead, we'll ask users to pick their favorite engine that they want to run on. What we are trying to solve is the stuff that goes beyond that. How do you develop these applications and how do you run? So the unified streaming API allows you to develop across Storm or other engines as well. Right now, we have a tighter integration to Storm. For obvious reasons, we have historical knowledge of how the Storm works. But we built a unified streaming API and a runner spec that allows users to develop their own runners as well, and we have plans to add more. So in the end, again, distributed streaming computation engine could be Storm and any other implementation. So again, the main use case that we are trying to solve is how you're connecting to your sources, how you're joining, and how you're doing the windowing aggregations and all that stuff. All those primitives we want to kind of provide, make it easier for you guys. So that's about where we are coming from. And one of the interesting things what we did is service pools and environments. So service pool, I will explain more closely when I'm going to do demo. The idea behind that is you have these clusters deployed here, and you want to make that configuration available to the application, bring that all the configuration into your application easier. So that's what we are trying to do. So quickly, I'm going to jump to a demo. So before I go into Streamline or SAM, I'm going to showcase our registry. So as you can see, these are the schemas that I registered. Some of them are Kafka, some of them are HDFS or whatnot. So you can you can go here and define your name description. Again, type right now we have Havro. You can change that. Okay. Better? Yeah. Yeah? Okay. So again, schema group, you can change it to, if it is HDFS, whatnot, and compatibility policies that you want to set to. So once that is set, it is asked you to input your schema text, and we're going to version that. We'll allow you to kind of evolve the schema. So schemas are set. That is one part of the equation. So you now defined what type of data in your Kafka or Kinesis or and other messaging stores. Ooh, you're setting the mood. So this is a SAM Streamline application. So what you're seeing is a bunch of streaming applications that are developed. So initially when the user lands, we want to showcase what are the applications that are running, kind of showcase the important metrics so that user can understand how the applications are doing, latency and whatnot. So before even developing the applications, the user need to do something called a service pool. So service pool, what it does is, let's say you have an Ambari cluster manager, you install a bunch of services. And essentially in a streaming application, you're probably reading Kafka from one cluster and probably interacting with HDFS and Hive in another cluster. So traditionally what used to happen is you need to know where the Kafka is running, what is your HDFS Hive configs. With service pool, what we can do here is, let me delete. So I have a Ambari instance running here. I'm just using the Ambari cluster URL here. I'm going to delete this before re-importing this. Okay. So it's going to ask me the credential for Ambari login. So it's going and talking to Ambari instance and asking it what are the services that this cluster has, and fetching all the configs of that cluster.
So this is what an operator, administrator would do.
Yes. So typically, service pool, the intention behind service pool is like you want a mirror of your clusters that your applications are developing, because that will be apparent once I go to developing an application. So once you have the cluster, I have 3 clusters here. One has Storm and Kafka, and I have other HBase and other services running. So as a developer, I can create an environment that my application going to interact with. In this case, I'm going to say, so in this case, I know my topic resides in Kafka here, and I'm going to run application on Storm here, Zookeeper. I want alerts and metrics for my application. I'm going to choose Ambari metrics from here. And I'm
connected with everything, and now it's just pointing, clicking, and.
So a little bit of context here. Traditionally, what used to happen, especially in, when developing an application like this, is you need to kind of go fetch where is my HDFS site, my core site, Hive site, whatnot, and package it in the jar while deploying into production. what we are doing here is, we are asking the operations guy to set up the service pool for us. And as a developer, I know what are the services that I want to, and I'm picking and choosing from different clusters, different physical clusters itself. So in this case, I'm going to use Hive HBase, that's HDFS, from these two clusters. So I created a new environment. In this case, it contains all the services as the developer that I want. So once we set this up, I'm going to go here and try to build an application. So in this case, we're going to ask what is the environment that you're going to build against. So we already have a bunch of these things. I'm going to select meetup. So now you have a topology editor. So now you know where you're developing against and what is the environment that you chose. So if you see on the side, a topology in this case, or a streaming application traditionally is a source, you have a bunch of process, and it's zoom in. Okay. So on the left-hand side, you have source, process, and sinks. These are actually not being repackaged or anything. We are using existing Storm components. Similarly, if you change an engine, you get to choose their own components. So we're not rebuilding anything here. We are just making them available to you. So in this case, I'm going to use, for example, Kafka. So once I click here, the thing that you've seen here, Zookeeper connection URL, is already filled in. That is because in my environment, I already picked Kafka as one of my services. So if I go here, so it also shows all the topics that are available in that particular cluster. So you're not, again, going back and running a command line tools to figure out what's going on there. So another thing, I don't know if you notice this, the output is appeared here. That's because I chose truck events Avro, and I already defined a schema for, let's go here, yeah, truck events Avro for here. So it's fetching that and giving you a context about what is your data that is going to be. So the challenges of any UI-based editor is you want to have a type-based information available to you, because you are building conditions, you are building process, you are building functions or whatnot. So you want to operate on the data so that you know what is this particular driver ID, is it integer or a string. So all that information is available to you in this context. This is typical Kafka group ID information. So I hit OK. Now I'm going to do a aggregate of this data. So once I drag and drop here, so now the output of the previous source became an input into this particular process. So aggregate, in this case, a window-based aggregate. So you can define your window and select a bunch of keys and apply UDFs on the data that's coming in. So in this case, I'm going to select driver ID as my key, and you can keep selecting and whatnot. And I'm going to use account-based window, 100. Ooh. That's nifty. And we're going to support processing time based or event based. So you can get to choose your processing time or any field that you think is a event based time. So the interesting thing here is, let's say I want to calculate a route based aggregation. Let's assume this is the speed. I'm going to do average of it. Okay. Right. So I'm just playing with the data here. So the aggregate functions here is a pluggable UDF functions. So we are supporting a built-in bunch of UDFs here. So as a user, you want to add your own UDF into it, you can upload it here, and it will be available for all the users who are using this particular application. So as I am doing this, there is an output schema is getting calculated for you, right? So this is, okay. So that's the aggregate window. So we have different types of process. For example, join. So I can drop another Kafka here. Let me take struct speed event. So again, the schema is fetched from the schema registry itself. Now I'm going to do join of two of these topics. So as you can see, we have two stream schemas that are appearing here. I'm going to select one stream, and I'm going to join based on driver ID join could be inner, and driver ID again it's a window-based join. So typical table join, you define your condition. Now you get to select your fields. In this case, it's a streaming join. So we're going to select a bunch of fields that we want. Again, as you're doing this, there is a output schema being called. And I want to do something more interesting based on this. So I'm going to attach a rule. So rule for us is a simple if-else condition kind of a rule. So in this case, I have the data that is coming in here. I'm going to add a rule 1. So let's say speed greater than 100. So what it does is you are joining two Kafka streams, and you're emitting that into a rule processor. In the rule processor, you added a condition saying that if this matches, you emit forward that event further downstream. So in here, I'm going to add, let's say, HBase, for example. So that rule process allows you to do not just one, like multiple rules. So whenever you connect that rule processor into any other things or any other process, we're going to ask which rule you want to select. You can get to select multiple. So what it does is basically any rules that getting matched will forward only those events into your downstream sink. So here again, the environments comes into place because you chose a stream inside. This particular HBase is coming from there. We're going to showcase all the tables that are available, and you get to fill in like column family or something like that. And another interesting thing is you can actually choose to send emails. We have a notification interface. This is going to be long form to fill in, but essentially what it does is, whenever the rule matches, you can send a interesting, emails and kind of alerts users or whatnot. And this is an extensible framework here. You get to add like your SMS or whatnot, your iOS notifications, whatnot. So this together.
So a couple of things. The processors, you can plug in, have your own processors. You can have your own aggregate functions, right?
Yeah.
They will show up on the cat.
So another thing is like we are showing all these building blocks on nice UI, but where we want to give control is a custom processor. So custom processor is, in our case, is you want to plug in your own business logic into it. So this is a custom processor. So where users can, so we have an interface and SDK, allows you to kind of develop your own version of what a processor means, and we will ask for what is your input schema, what is your output schema in the custom processor. And you can add, user. So this particular section is defining what user going to input when they see this in topology editor. For example, this is a WebSocket sync. What it does is it takes an event published into a WebSocket. So I'm asking user to input me user ID, password, connection URL, and a WebSocket topic name, right? So I registered this. Once I registered this, you can go back to your application. You can see that appearing here on the WebSocket sync, right? So I'm going to use this, drop, connect. So all the fields that I asked for are appearing here. And user can input, and whenever this event comes in, I'm going to publish that event into a WebSocket topic name that user gave me. So that's so now that's the development part of the equation, right? So let me go back to a topology that is running. Okay. So this is a running topology that is already deployed. It's running on Storm cluster right now. So this is where we call as a view mode, or an operations mode, where user can see, or a DevOps can see all the metrics that are flowing through. Right now we are only showcasing some of the metrics, but the idea is to kind of add your own metrics into it, customize this page so that you want to look at what are the critical metrics that are important to you and manage that page. So this will allows you to kind of create alerts saying that if there are failed tuples more than X number of times, shoot me an email. So all your monitoring is being handled here. The interesting thing here is we made this more, again, on the backend part of it. Whatever the metric storage you use, we will end up supporting that. Right now we support OpenTSDB and Ambari metrics. You can easily swap with the Grafana if there is an API available for that. so that we, as a user, you can come here as a one-stop gap to monitor your application and develop your applications. So looking more into this is, for example, this topology is reading from 2 Kafka topics, doing a window-based join, and writing a violation rule. What it's doing is you have truck data that's coming in and a speed events that is coming in. They're joining for X number of seconds and emitting that into a rule processor. It checks if this is a violated event. That is, there is a traffic violation happened for this driver, right? And now we want to derive analytics out of that. So we're publishing all these events that are matching that rule into a Druid data cube. Once the data is published, we have something called as dashboard view. Okay. Let me go ahead. So I missed the link, but here's the superset view. So all the data that you are actually publishing here by this particular topology, where is it? So the data that's going in here, we have a superset that can allows you to kind of create this dashboard. Basically, all the data that is being streamed in, getting converted into what are the charts that you want to kind of expose to the users. So essentially, we are saying that application developer get to develop your application, get it to deploy. As an application monitor or the DevOps guy, you can monitor your application using the view mode. And finally, on the data analysis part, will allow you to push into Druid or different analytics platform that you will choose to. And we have a UI on top of that that allows you to create these charts, interesting charts that will make you understand what is this data that you are processing to. So in this case, we have a bunch of violations coming in. We have a table view that is kind of aggregating per user who has a lot more violations than others. And more interestingly, here at the map, you have actually, since we have a latitude and longitude data coming from the Kafka itself, we're able to plot where the violations is occurring more. So that's the 3 parts that we are aiming to solve, and that's Streamline or SAM. So more on this. So we do have a custom processor SDK. So we allow users to plug in their code into it and allows you to write your own UDFs or notification syncs. So that's about that. And of course, an open source. We did a 0.4 release, and we are heading towards adding security and other features. And it's going to be a 0.5 release in May 31st. Again, it's Apache licensed, and again, we're looking to incubate this project as well. And if you are interested in using this schema registry, please reach out to us. We are happy to work with you. Kind of, if you are trying to use it, trying to contribute it, please reach out to us, and we'll happy to help with that. So yeah, that's pretty much it. Any questions? Yes.
Oh, yeah. Is it this way? Cool, thank you. So it seems like this SAM thing is dependent on everybody running HTTP. So you guys are going to be like launching Storm and doing everything inside of your ecosystem?
No, actually, we're not trying to do that. So I think one thing that I missed saying that is not everybody is going to run HTTP or Ambari. What we have is a nice integration to Ambari, but that's a pluggable interface. We are working on integrating into Amazon services so that you can paste Amazon URL, we can pull in that services, as well as we do recognize that people want to manually manage like Puppet or Chef based on this. So you can manually add your configs and everything that will make available to your application itself. So, sorry, go ahead.
Okay, so I was just going to ask about like how you actually launch into Storm. So like we have a wrapper service around Storm. So in order to use something like this, we need some way to tell you, hey, when you want to take your topology and run it, you got to call this like endpoint and provide a bunch of parameters in order to get into our cluster.
Yeah.
Otherwise, like we don't let you in.
So right now everything is driven by service pool and environment. So right now this particular topology is running already deployed. So we have a deploy button right down here. Let me show you that.
So when you define the service pool, right, when it imported Storm configuration, that tells you where Storm, Nimbus is running, what configuration to use. You not only pull it out of ease of use from Ambari, you can also add a Storm service manually. And once you define that, that becomes available for anybody to run the application.
And sorry to belabor the point, but could I define that, oh, you need to hit this HTTP endpoint and like, post your jar? Like we don't accept like people talking directly to the Nimbus for launching their jars. They got to go through our thing where they provide like an API key and stuff like that, so we can kind of gate the stuff.
So in this case, we have a test cluster, manual cluster. So if I choose Storm, we're asking a bunch of server names here. So we usually use Nimbus, but what this actually being generated is based on a spec file. It's a JSON spec file, so we're not hard coding anything into the UI. So in your case, you want to post this jar into a Storm service, you get to define your own service. For example, we have custom way of adding your own service as well. So instead of you don't want to use Storm, you get to add Storm my own service kind of thingy, and you get to define what is the endpoint that this jar needs to send it to.
Okay, cool. So then I could like create my special Storm and have one of the keys for this thing, or excuse me, one of the fields be like API key, and then our users would be like, okay, cool. I know my API key is this, and when they use the service, they'd plug it in.
Yeah.
Okay.
That's
cool.
great.
Thank you. Sorry. Next.
Yeah. So.
Make it easy.
So my question was about how you configure the number of workers and executors and stuff for each component in that topology. You're kind of building on the fly there.
Yeah. So load up. So we have parallelism unit exposed here, point 2, and we have customizable topology configurations. So again, this is, we just exposing a few of the stuff. Again, this is driven by spec files. So if you want to expose some critical property to the end user, you can just add it there, and it will show up here.
So is it possible to add ML or deep learning algorithms for analysis in this?
Yeah, so that's a good question. There are a lot of stuff I couldn't cover everything, unfortunately. As I said earlier, talked about ML registry. So when we are looking at registry as multiple components, so we looked at ML registry. Right now we have integration into a PMML model. So we expect users to kind of train the model and upload that model into our registry services. Once you upload that, we have a PMML processor that will allow you to select. In this case, I have a driver violation prediction model. I get to select, define my inputs in this model and what is the output to be expected. Right, so training ML is kind of a most often is an offline process that you want to do that, and you want to apply that model while you're on your streaming data. So PMML is one of the things that we are doing right now, and we want to work on. We are working on adding a POJOs, ML POJOs as well. So that is our approach to adding the ML.
Service as well.
Yeah.
If you deploy models somewhere else, you can interface with them using REST APIs. So those are the 3 ways.
All right, hold on. When you want to watch this again, you're gonna be really thankful for this.
By the way, do you have any plan to include a Flink in your HTTP future distribution? Flink.
I can talk about the Streamline plan. Storm is where we are putting our efforts into. But again, it could be a possibility that it might be happening. So we already defined the spec on how to add a runner. So what's happening is when you actually hit the deploy, we have this DAG model, similar in terms of Beam. So we have runner as an interface. Right now we have a Storm runner. It takes this DAG, goes and visits, converts that into a topology, builds a jar on the fly for you, and packages all your necessary configs together, builds a bigger jar, and sends it to remotely to whatever your configure servers are. So typically, same thing will happen with the Flink, goes through this and converts that into a Flink equivalent topology.
It's like design time, runtime. So it's the design time, and then you can pick up the runtime environment later.
Yes.
So the PM ML you mentioned here, so the module here you said is supposed to be offline, and in streaming, won't it be like a common use case where people would want to update their models in a streaming fashion as well?
So yes, that's how we are looking at a registry as well. So there is two ways to do that, right? So one is like you're having a batch-oriented or an offline process that's keep training with historical data, not just the streaming data, to get a better accurate results. And once you get a better model, you update your registry with that model, and this processor can pick up on the fly to apply that model. That's one thing. And obviously there is online ML models that people want to use. So we are exploring that as a different processor itself, but not into the model. So traditionally what we have seen so far is most often people try to train their models offline and then use that model on streaming data. Sure.
I guess I might get my workout.
I'm curious, what's the underlying mechanism behind how the registries are handled through after our processors finished processing data? Like, are there intermediate schemas registered?
So NiFi does that. So NiFi integration.
The question probably is
how
your schema is evolving. Are those schemas getting registered?
Right. Are they getting registered to schema registry, or is there some sort of mashup that happens that?
Yeah. So it is. So for example, if you want to, we didn't see that as a necessity to register intermediate components. For example, joint processor schema, I don't think you would use anywhere else. What we are trying to do is, like, for example, in the end, you probably want to write back the data into Kafka topic, for example, right? So whatever the okay. So this is the end point where you are process some of the data. Now you're pushing back to Kafka, Druid, or whatnot. So this is where we want to enable further use cases. So any data, that schema that is coming to Kafka, now will get automatically registered into your schema registry. So as a user of, or a developer of this topology, you are enabling other users to use the end data to further process or develop further topologies. So you're registering this schema and you're making available into another topic, or for example, another user comes in, want to consume the data that you are ingesting to, will have the schema available to them.
Yeah, I think as the schema evolution is happening when you're doing the processing, that schema evolution is useful only for you to continue to build that process, right? What data you have, how to process it. And if you want to publish it to Kafka, that's when it automatically gets registered in the schema registry. We are also considering looking at building some kind of taps, right? That you can say, here is the data ready enough for it to be consumed by somebody else, right? All the intermediate steps have happened, and I want to publish it at this point in time. Even that will be possible. Again, that's going to happen through Kafka.
Yep. So you can attach this thing anywhere in this topology to publish back into the Kafka.
You can import and export. So even if you have a big overlap, you want to change a couple of things, these two.
Yep. You.
I was going to ask, like you said, import and export?
Yeah, you can export these into
like into some.
Is it JSON? It's JSON.
Yeah, I mean,
yeah, just this whole topology as you build it. So then that way you can put that in like version control, and you don't have to worry about
we get
rolling
version.
back in problems.
We do version. So little bit context behind that is the import and export, for example, especially with environments. Typically, what do we see is a dev cluster, QE cluster, then a production cluster. As a dev, you don't have access to production cluster. You developed your topology against the dev cluster. You tested it, handled to QE. So while importing, we're going to ask which environment you're going to pick. Importing.
So the dev exports it, gives it to QE, they import it, right? So and it just goes on to another environment.
Yeah, and so also we are providing versioning as well. So each time you make a change, we auto-save that and allows you to kind of look at different versions, V1, V2, kind of, it goes incrementally. So any change that you're getting deployed into production gets as a version, so you can quickly change back to something went wrong, change back to a low version.
Nothing ever goes wrong.
Yes. He will disagree. Yeah.
That's not what Sam.
He was not listening to that session.
So,
Is registry being stored in memory?
no.
What to do if it's not, right? It's yes or no?
It's no. We're not storing in memory. We are storing into a persistent storage. MySQL, Postgres support is there. Phoenix support is there. We have a pluggable storage manager that allows you to, for example, right now we are supporting MySQL, Postgres, Phoenix, and if you want to store your own database, you get.
Oh, it's like database. So let's talk about model. So if the whole model cannot be fit in the whole memory, what to do?
Which ML registry model? ML model?
Doesn't any sort of model, the machine learning model or deep learning model. I assume the typical cluster does not using any sort of memory grid. So it's not a uniform memory.
Yeah.
So basically on the machine learning model, what you're pointing is like a descriptor where the model resides, right? It could be a file, but it could also be on a distributed store.
Yeah, but to be honest, eventually file will be very strong. Let's say it's a database. It's a special file structure. But when you are serving the model, you have to read your model from a database or a file or any sort of storage to the memory because you want to make it faster. That's the reason. So when we are serving the model or we are training the model, trying to store something, the model is like a live model. So you have to be quick. If you are storing the database, that's too slow, way too slow. So that's called as in-memory model.
Yeah, I know what you mean. So right now it's in memory, yes. You can have it live in a distributed storage, but
It's a similar situation. You are storing metadata there, right? So metadata can be in database, in file, or in memory. Right? Memory is faster.
just like anything, right?
Yeah, just like anything.
Yes.
It is really late. Thank you guys.
Yeah. Thanks.
Yeah. So just a couple announcements before people leave. So thanks for coming out. We're looking to have more meetups around this stuff. So we want to have some meetups that are more hands-on. So look for some of the deep dives that are going to be coming. There's also the DataWorks Hadoop Summit that's coming, and there'll be more sessions there. And as things progress. So thanks for coming out. Check out the meetups. More stuff will be coming.